Okay, good morning. And I see that only about half the class is there. Get started. Yeah, I just want to remind that today's afternoon class, the lab class will start at 3 o'clock, not at 3:30, because I have some other meeting at 4 o'clock. Okay, so please join at 3 o'clock itself. Your tutorial 2 is more or less evaluation is complete. Mostly sometime today or tomorrow we'll release the marks for the tutorial 2. Then we have been receiving lots of requests for this regrading of assignments 1, 2, 3. I'm going to have a discussion with the teaching assistants tomorrow. Actually, it's not possible to redo the grading completely for all the batches. Okay, so we'll look at the requests that students have sent, and then only kind of genuine request we will honor. Okay, yeah, if they're minor, I think no, will not go through the process of the regrading. Okay, that I'll tell you maybe sometime later, maybe on Wednesday. Okay, or you will get the response to your requests. Okay. See, if it's only 1 or 2 marks out of 50 that you are losing, don't worry about it, because that will be scaled down to 10 marks mostly, right? So you'll not really lose much of marks. Okay, so let's not be kind of getting worried about losing 1 or 2 marks out of 40 or 50. Okay, if you're losing only significant marks, right, then we'll look into it. Okay, and I just want to announce that we'll have one more tutorial on next Wednesday. That will be on the next Thursday. That will be on the 5th of November. And the topics for that tutorial will be whatever is going to be covered till this Wednesday. Okay. So that will be the tutorial 3. And mostly I'm planning to wind up the classes sometime next week, right? And if that happens, then we'll have one final tutorial on the 12th of November. That will be kind of a makeup tutorial. It's not compulsory for everyone to take. Only those who got less marks or those who could not take any one of the tutorials, right? They can take this tutorial, and then finally we'll select the best three out of the 4. Okay, and the syllabus for that tutorial 4 will be the complete course syllabus. Okay, because it's a kind of a makeup tutorial. There is a question about any update on the NSEMs and the TCS centers. Not yet. I think that's being explored. I think sometime later this month or maybe early November, we'll have some confirmation about that. So still the plan is to conduct these NSEM exams at the TCS centers sometime in the last week of November. Okay. I guess you will be given at least about 2 weeks notice about the end semester examinations. Okay. Yeah. Any other questions? There is a question if we'll have an NSEM exam. Yes, there will be an NSEM exam, but that will be a written exam. Okay. And mostly that will be conducted at the TCS centers if that works out. Okay. Yeah. Any other questions? And the lab course will release the final assignment mostly sometime today after the lab class. If possible, I will do it today or latest by tomorrow. Okay. And you'll be given time till 9th of November to complete the assignment. So that will be the final assignment in this course. No, Vishnu, I don't think it's going to be easy for me Okay, it requires a lot of background preparation to be done and a lot of support from the TAs. Okay, I don't think it's going to be easy. I know that it's being done for the PDS course. Okay, yeah, yeah. Okay, fine. Any other questions? Okay, let's move on then. Yeah. So in the last class, we were looking at the typical instruction set of a RISC processor or a load store architecture processor. So we've seen that there are some simple instructions like the increment and the decrement of a register, then move from one register to another register, compare the contents of the two registers, move a constant value to a register, move the address of a variable to the register. Then there are going to be several arithmetic and logic instructions. What I'm giving you is only one instruction of that type. So typically, all the arithmetic and logic instructions will have three operands. All of them will be registers, and two registers will be the destination operands and source operands, and the third one will be the destination operand. And when it comes to the load and store instructions, where we are typically performing a memory read operation or a memory write operation, there are a number of ways by which the address from where the read operation or the write operation has to be carried out can be specified. These different ways are what are referred to as the addressing modes. And if we give the address of the memory variable directly in the load instruction or the store instruction, that will be referred to as the direct addressing mode. Actually, it should be called as the memory direct addressing mode because we are giving the memory address. And sometimes we can have the address of a variable in a register, and then we specify that register as the argument for this load instruction. And typically we put this register name in the brackets, square brackets. Then it indicates that it's a registered indirect operation because now the register contains an address, not a value. And one has to get the address from that register and then perform the memory operation. And to support the data structures like the arrays, we'll have two registers. One is the base register and the other is the index register. So typically we have to add the content of the index register to the base address to get the address of an element of an array. Okay. And to access an element of a record, which is a field in the record or a struct, right? We go for the base relative addressing mode, where again there are two parts. One is the base address, the other one is the offset from the starting address of the record, right? And when we add both of them, right, we'll get the address of the field in the particular record. So this offset is typically referred to as the displacement from the beginning of the structure. And whenever you are dealing with the array of records and then you want to access a field within a record which is an element in the array, right? So typically you have three parts here, right? So the base address of the array, then the you need to get the starting address of the particular record, and from that, what is the displacement? So typically there will be three parts here, and this addressing mode is what is called as the based indexed relative addressing mode. And we can have these things as the memory operands for the write operations as well in the store instructions. Then we have seen that there are control transfer instructions like the unconditional jump and the conditional jump instructions. Then you have the function calls and the return from the function. Then pushing the content of a register onto a stack and popping the content of a stack onto a register. Okay. So typically these are the instructions that will be there in a processor, and the format that we are given is for the RISC processor architecture, because in the RISC processor architecture only the memory operands will be allowed only for the load and store instructions, and for all other instructions, no, it will be register operands. Of course, the exception is this move address, where you have to give the address of the variable. Okay. Yeah. Any questions about this? Yeah. So what you're given here are the typical assembly language instructions, and the set of all instructions put together is what is called as the instruction set of the processor. And typically the instruction set architecture of the processor specifies all the instructions that can be executed by the processor and all the addressing modes that will be supported by the processor. Okay. And typically each processor units of RISC processor type, the instruction set architecture will be different from one another, right? Because the formats of the instructions can be different, address modes that are supported can be different, and so on. And you will study some typical processor instruction set architectures in the next course. Okay. So what you are given is actually the format of the instructions in the assembly language for a particular processor. But typically, when we compile the high-level language program and then you want to generate the machine code for that, the compiler will go through this intermediate stage of representing the high-level language program in terms of the assembly language instructions, and then representing each of these assembly language instructions in the binary form that will be called as the binary representation of the instructions. So typically, you have to specify the different operands of the instruction and the operation to be carried out by the instruction in the sequence of bits, right? And what you're seeing is for a few instructions in the last class. So if you take the increment RA instruction, so there will be an opcode field which specifies that it's an increment operation. And here there is only one operand, so we need to specify the address of that register. In this case, the address will be the I, right? If there are two operands like the move RI, RJ, again there will be an opcode, then the address of the first register, address of the second register, and so on. So it will be similar for the compare also. And in the case of the move immediate, it will be opcode, then the register address, then whatever is the constant that will be stored by the move instruction into the register, right, will be specified depending on the number of bits taken for the opcode and the specification of the register address. The number of bits the constant can take will be determined. So typically it may be about 15 to 20 bits. It all depends on what is the length of the opcode and what is the number of registers that are there. That decides the register address. And the remaining bits, typically if the whole instruction is for 32 bits, the remaining bits will be used to specify the constant that will decide the range of values the constant can take. So typically it will be a signed value, so it can be positive or negative value, and it will be a 2's complement representation that will be used. Okay, and the move address will be, again, we'll have the opcode, then the register, in this case the destination register, right, and the address of variable. So it will be a memory address, and typically the memory address of a variable can be very large, right, 32 bits. So there are different ways by which we can specify the address of the variable, which will be specified partially in this instruction here, and the remaining bits will be specified through using another mechanism. Typically there will be another register that's explicitly identified to specify the part of this address of the variables. Again, we will study that in the next course, so I'll not go into the details, right? But we can get the address of the variable information by using the content of this field and using the content of maybe another register, which is set aside only for that purpose, right? And then one can get the address of the complete address of the variable. Okay. Now, when you look at the typical arithmetic and logic instruction, again, the opcode will specify which arithmetic or logic operation that you want to carry out. Then you'll have the K here, that is the address of the destination register, and I here and the J here, because all these K, I, and J refer to the register addresses correspond to the operands of this instruction, right? And typically this will be less than 32 bits, okay, because the register field will be 5 bits or 6 bits, then the opcode will not be more than the remaining bits, right? So you can see that the format of the instruction for the arithmetic and operations is fixed and it's uniform, right? And typically it will be one less than 1 word in length. Okay, yeah. So now when it comes to the load instructions, there are different pieces of information that we need to specify depending on the type of the addressing mode. So again, there will be an opcode which indicates that it's a load operation. Then there will be a few bits that specify what is called this addressing mode. Typically, it will be 3 bits because there will be more than 4 combinations of the 4 different addressing modes, right? So those 3 bits will specify whether it's a direct addressing mode or the register indirect addressing mode or based indirect addressing mode or so on. And accordingly, one can look at the content of the remaining part of the instruction, right? So if the addressing mode indicates that it's a direct addressing mode, we are going to have the address of the variable here, right? If it is a register indirect addressing mode, again the opcode will specify that it's a load operation. Then the addressing mode of source operand, right? Then the source operand specification itself, right? And the destination operand specified, right? So the addressing mode will indicate that it's a register indirect operation. Then the J indicates that it is the source operand register, right? And the I indicates that it's a destination operand register. Okay, so you can see that though it's the same load instruction, depending on the type of the addressing mode, right, the different fields in the instruction can be different, right? And accordingly, the corresponding parts of the information available in the instruction have to be accessed, and then they have to be used in performing the memory write operation. Okay, so I leave it as a small exercise for you to figure out the formats for the other types of instructions, right, which are required depending on the addressing modes. Okay, and when it comes to the jump instructions, so typically we will have opcode, then the address of the label. So basically, it's the address of the instruction associated with that label, right? And when it comes to the call instruction, again, it will be opcode, right? Then the starting address of the function. Okay, so depending on the type of instruction that you're dealing with, the format will be slightly different, right? And one has to look at first the opcode field and then interpret the remaining bits in the instruction. So all of this will be done by one module in the CPU that will be called as the instruction decoder. And it's also called as the control unit. So the input to this instruction decoder will be the instruction, right? And typically this instruction will be available in another register called the instruction register. Okay, so whenever an instruction is fetched from the memory, that instruction will be stored in this instruction register. Then the content of this instruction register will be available to the instruction decoder. Then instruction decoder will have all the necessary logic to look at the different parts of this instruction and then decide what type of instruction it is, and then what action has to be taken in order to carry out the operation to be done by that instruction. So typically this instruction decoder will generate the various control signals that will go to the other components in the CPU, like the register file, then the ALU, and it will also send the necessary control signals to the memory unit, indicating whether you want to perform the read operation or the write operation from the memory unit. Again, we'll come back to those details a little later. Okay. So this instruction decoder is actually kind of set to be the heart of the CPU. Okay, because even if it makes one small mistake, right, in interpreting the instruction and then generating control signals, then a wrong operation will be carried out, right? Actually, most of the time that's spent for designing a processor is actually spent in the design of this instruction decoder, because there will be several dozens of instructions, and the instruction decoder must perform the necessary operations, right, for all these instructions without any mistake. And typically, this instruction decoder is the most complex part in the processor in terms of the logic that's to be incorporated. Okay, I mean, in terms of the number of gates and all, maybe the arithmetic unit may be more complex, but in terms of the operations to be carried out, right? Typically, this instruction decoder will have the most complex operations to be carried out, because it has to deal with the differences in the formats of the instructions and so on, right? And for every instruction, depending on that instruction, it has to perform the necessary operations, either to fetch the operands, then carry out the arithmetic or logic operation or the memory operation, then put the result in the destination operand, and so on. Again, we'll see some details of that in the lab course, right? Again, it will be discussed in more detail in the next course, in the computer organization and the architecture course. Okay, yeah, any questions about this? Okay. Now, given a high-level language program, the compiler will perform this task of converting into the machine code. And what is the machine code? Machine code is nothing but the binary representations of instructions, right, in the so as you have seen, every high-level language program statement will be converted into a sequence of instructions. So when you compile a high-level language program, the complete instruction sequence corresponding to the sequence of statements in your program will be there. And in that sequence of instructions, every instruction will be represented in the binary form. These binary representations of the instructions put together will be called as the machine code for the particular program. Okay. So it is the responsibility of the compiler to generate this machine code for any given high-level language program, right? And again, how it is done, you'll be studying in more detail in the course on the compilers, right? Right now, what we are going to look at is, once this compilation is done and the binary representations of all the instructions in the sequence of instructions corresponding to program is available to us, how to execute this in the given processor architecture is what we are going to quickly look at, right? And we'll get some understanding of that. Okay. Now let's say for a given high-level language program, there are some number of instructions. I'll call them as simply I1, I2, so on. IN. So it is this sequence of instructions. Right now, I'm assuming that there are no jump instructions or no function calls and so on, right? Because typically, if there are jump instructions or the function calls, right? Typically, the execution of instructions will not be exactly in this sequence, right? They'll be going through the part of this instruction sequence in number of iterations, and sometimes there will be deviation to the start of the function. Then you go back and you go and execute that function, then return back to the main program where the function is called and so on, right? And you can have the nested functions and so on, right? So I'm not talking about any of those cases. So if I have a simple sequence of instructions correspond to a high-level language program, how does this sequence of instructions get executed in the processor is what we are going to look at, so that we understand the different operations. Then we'll see how to make this execution of instructions as fast as possible. All right, that is the target of the discussion actually in the design of the computer system. Okay, first let's look at the basic operations in the execution of any instruction. As you can see, typically the execution of instruction will involve fetching that instruction and then performing the necessary operations. Okay. So typically after you compile the program, the executable code will be available in a file in the hard disk. And whenever you start running the program, right, the content of that executable file will be loaded into the memory, right? And typically it will be loaded into what is referred to as the instruction memory. Which will be part of the main memory in the system. Okay. And it will be stored somewhere in the instruction memory, and the address at which the code is available will be known to the operating system, right? And the operating system, when it starts executing this program, it will load the starting address of this code into the program counter, right? And one can use the content of this program counter to go ahead and then perform the fetching of the instructions. So the address of the next instruction to be fetched is available in the program counter. So that address will be sent to the instruction memory, and then we'll perform a memory read operation. And when we read from the memory, what is it we are going to get here? We are going to get an instruction which is available at that address, right? And that will be made available in the instruction register, right? So basically this instruction fetch operation involves taking the current content of the program counter, sending that as the address to the instruction memory, then perform a read operation. Then whatever is the content of that memory location will be the binary representation of that instruction, and that binary representation of the instruction will be stored in the instruction register. And this instruction register contents, as we seen little earlier, will be sent to the instruction decoder. Actually, this instruction decoder is not same as the decoders that we have seen earlier, right? Because there we are talking about some 3 to 8-bit decoder and so on, right? And this instruction decoder is completely different from that. It's actually a very complex logic, right? And the purpose of this is to take the contents of the instruction register, which is a binary representation of instruction, and then generate the necessary control signals that will be required to perform the operations that are specified by the instruction. Okay. So the modules that are involved in this instruction fetch are the program counter, instruction memory, then the instruction register, right? So let's mark it here. And typically after the current instruction is fetched, there will be a mechanism to increment the content of the program counter so that it will point to the address where the next instruction in the sequence will be available, right? And only when there is a jump instruction or a call instruction, the program counter contents will be loaded with the address of the jump instruction's target address or the starting address of the function. Otherwise, typically it will be incremented by 1 so that it will point to the next instruction address in the sequence of instructions. Yeah. Any questions about that? Okay. Now let's see, where do these control signals go to? So typically these control signals go to the other components in the processor and the system, right? So the other important components in the processor are the register file, which we have seen earlier, right? And what are the operations that we can do on the register file? We specify the register address, right? And typically we perform either a read operation or the write operation into the register. I mean, reading from a register in the register file or writing into a register in the register file, right? And if it's a read operation, the data will be fetched from the registers. If it's the write operation, the data will be provided and that data will be written into the particular register whose address is specified, right? So the three important interface components for this register file are the register address, then the read write signal, then the data bus where the contents of the data to be written to the register or the data that's from the read from the register will be available, right? And these control signals about which register has to be accessed and whether it is to be performed by read operation or write operation will be specified by the instruction decoder, right? Let's say if we have an instruction like move immediate or 575, right? So the binary representation of this instruction will be there as input to the decoder. Then it will identify that it's a move immediate instruction. Then it knows that it has to get the value that's there as part of the instruction, which is 75, basically the binary representation of 75. That will be stored in this register R5, which means that it has to perform a write operation into the register 5. So the value of this constant 75 will be made available on data line. The register address will be specified as 5. Then it will say that perform the write operation. So all this piece of information will come from the instruction decoder to the register file, right? And then the other major component in the CPU we have seen is that the arithmetic and logic unit, where typically there will be two source operands, operand 1 and operand 2. Right? Source operand 1 and source operand 2. Then you specify the operation to be carried out using few bits, right? And typically you will have this arithmetic and logic unit consisting of circuits for performing the operations on the different sizes of the operands, like it can be a byte operand or a 16-bit operand or 32-bit operand or 64-bit operand, right? So there will be a few bits to indicate the size information. And depending on the operation to be carried out and depending on the size of the operands, the source operands will be passed on to the corresponding part of the ALU, basically the corresponding circuit in the ALU, which we have seen, right? And then this ALU will generate the result, right? Let's see if I call it as the out, right? And where should this output of the ALU be sent? So typically the arithmetic and logic unit is involved only for the arithmetic and logical instructions, and the operands for any of these arithmetic and logic instructions in the RISC processor is only the registers, right? So the output lines of this ALU will be connected to the data bus of the register file. So basically this will go to the register file, right? And where are the source operands going to come from? They'll come from the register file, right? So typically if you have an instruction like add R2, R0, R1, right? when the control unit gets this instruction and its binary representation, it sees that the current instruction involves performing the add operation on the contents of the registers R0 and R1. So it will send this R0 address and then perform the read operation, get the data, and then put it in the source 1. And it will fetch the content of the register R1, then perform the read operation, and then get the data and then put it as the source 2 if it has got only a single read port. If there are two read ports, right, then we can perform this read operation on both register 0 and register 1, and then get the data simultaneously from them, from the corresponding registers, and make them available as the input source operands for the ALU. Then the then the add operation says that the opcode, the operation to be carried out is the add, so that will be indicated by a few bits here. Then the size information will be indicated. Again, actually that should be part of the add instruction. So once all these pieces of information are available, then the arithmetic and logic unit will carry out the necessary arithmetic operation, and then it will produce the result. And once it produces the result, then again the control unit will specify that the data available from the ALU has to be written to the register 2, and that involves specifying the address as 2, then performing the write operation, then taking the data out of the ALU and then put it on the data lines of the register file. So all this sequencing of these operations is to be done by the control unit, right? And it will have all the necessary logic to sequence these operations. What do I mean by sequencing the operations? Whenever you need to perform the execution of the instruction, there are a number of sub operations to be carried out, like reading the contents of the registers, of the source operands, then performing the arithmetic operation, then putting the result back into the destination operand register, right? So these are the sub operations. So each of the sub operations will be carried out step by step by the control unit, and once the instruction is complete, right, then it is ready to go ahead with the execution of the next instruction. Okay. So typically, the control signals that are required to perform this arithmetic and logic instruction will be generated by the control unit, and then it will be sent to the arithmetic and logic unit. So this is only for the arithmetic and logic operations, but typically you also may have to do the memory read write operations for the variables, and that will be done in another part of the memory called the data memory. That's where there will be memory addresses assigned to the different variables in your program, and typically you will read the values of the variables and then process them and then put the result back into some of these variables or some new variables. So the operations to be carried out are the read and write operations, where again we specify the memory address. Then we specify whether we want to perform the read operation or the write operation, right? And again, if it's a read operation, we are taking the data from the memory. If it's a write operation, we will be sending the data into the memory. And again, the necessary control signals will be generated by the control unit. So typically, this is required for the two operations or two instructions. Let's say if I have load RA, X, or let me take it a specific thing. Right? So if it's a load R0, X, then the address of source operand is the address of the X, so that will be sent to the data memory. Then it says it will perform the read operation because it's a load instruction. Then once the data is available from the memory, right, it will be written to this destination operand, that is the register 0. So the load instruction will involve two units. One is the data memory unit, the other one is the register file. Similarly, the store also, we get the contents of the register R1, which is there in the register file. So we had performed a read operation on the register file. And then that data will be passed on to the memory unit, and we also specify the address of the Y here, and then the operation will be indicated as the write operation. Okay, and if any addressing mode is involved, the control unit will do the necessary operations to get the address of the complete operand. That is, if it's a based index addressing mode which corresponds to an element of the array, Then you add the content of the base register and the index register, get the address of that element. That address will be sent to the data memory. And once that element value is available, then that will be put into the register, which is specified as the destination operand of the load instruction. So again, depending on the addressing mode, what operations to be carried out will be different, and those operations will be carried out by the control unit. So that's why we see that the control unit becomes very crucial, right? Because depending on the operation to be carried out, depending on the format of the instruction, right, one needs to perform different kind of processing, right? So the set of control signals to be generated will be different. So all of that will be taken care of by the control unit. And once you design all these components, right, that is instruction decoder for the particular instruction set architecture of the processor, then the register file, depending on the number of registers that you have and the width of the registers, then the arithmetic and logic unit, which will have the necessary circuits for performing the logical operations, then the integer arithmetic operations, the floating point arithmetic operations. So all those circuits will be there in the ALU. Then the instruction memory and the data memory, which will be part of the main memory. So all this put together is what is referred to as the microarchitecture of the CPU, which basically includes the control unit, the arithmetic and logic unit, then the register file, the other registers like the program counter, instruction register. There will be a few more registers like the stack pointer and so on, right? So the circuits that are required to implement each of these parts of the CPU will be put together, and all of that is what is called as the microarchitecture of the processor, because you have the complete circuitry for the different parts of the CPU implemented at the circuit element level. That is, basically it will be at the logic gate level or the flip-flop level, and which in turn are implemented using the transistors, right? And typically this microarchitecture corresponds to the complete circuitry within the processor. And in the current day process, you will have part of the memory in the form of what are called the cache memories. I'm not going to discuss this in detail now. And typically there will be a separate cache memory, which is referred to as the I cache for the instructions, and there will be separate cache memory called the D cache. Basically, it stands for the data cache. Okay, and that will be part of the CPU in most of the current day process, right? So all this logic put together is what is referred to as the microarchitecture of a CPU. And obviously, the CPU itself is the central element in the computer system, and the design of this CPU is the most crucial part in the design of the computer system. And how it's designed and how well it's implemented forms the basis for the performance of the system, right, which we are going to quickly see, right? And the significant part of the time spent in designing a computer system is actually in the design of this CPU, okay? And typically the CPU will be different for the different companies. Like you have the Intel companies CPUs, you have the Motorola companies CPUs, and so on, right? And they'll follow different instruction set architectures, and then they'll follow different instruction formats, right? And therefore the design of these control units will be different, and the way this ALU is also designed will be possibly different in the different process. Okay, so the design of the CPU specifies the microarchitecture of the CPU, right? And the way it is designed will define the performance of the system, mainly because the CPU is the main component in determining the time it takes to execute the program. Okay, yeah. Any questions? Okay. What we are going to see next is different ways in which this sequence of instructions can be executed. I mean, what do you mean by different ways? We'll come to it quickly, right? But the target of any computer system, and mainly that of the CPU, is to have as much of throughput as possible. All right? And what do you mean by throughput? One can talk about the throughput at the different levels, but in the current course, we are talking about how many instructions are executed in a unit time like a second, right? So the throughput of the processor is typically specified in terms of the number of instructions executed in a second, right? So typically you would have come across the performance measures like millions of instructions per second, or nowadays we are talking about giga instructions per second, right? So what is we are talking about now? The processor performing the execution of the sequence of instructions in such a way that the number of instructions that can completely executed in a unit time like a second will be a few millions or a few billions, right? Now, if you just work back, if I want to realize, let us say 1 million instruction per second throughput, the time available for the completion of the execution of an instruction is going to be 10 power minus 6, right? Which is 1 microsecond, right? That's not really a big problem because we have seen that the delay of the arithmetic and logic unit will be a few hundred times the delay of the logic gate, and the delay of the logic gate is typically a few picoseconds. So completing the next execution of the instruction at the rate of 1 instruction per microsecond is not really difficult, but when it comes to realizing the throughputs of 1 giga instructions per second, that is, the time available for execution of the an instruction is only 10 power minus 9, which is 1 nanosecond. All right. So, is it possible to really perform the complete execution of an instruction within 1 nanosecond? All right. If we have to perform the execution of every instruction within 1 nanosecond, we have to see how much time it will take to perform all the necessary operations involved in the execution of the instruction. Okay. So in order to understand and then see whether it's really possible to perform the execution of instructions with such a high throughput, right? Let us look at the typical execution of the instructions in a simple way. This was what was done in the very early processors in maybe 60s and 70s, right? What do you mean by sequential execution of instructions? If I have an instructions like I1, I2, so on, IN, first we execute instruction I1. After we complete the execution of the instruction I1, then we start the execution of the instruction I2. Then we perform the necessary operations for that. And then we continue this until we come to the last instruction, right? Now, how much time the execution of these instructions will take depends on how much time each of the instructions will take to execute, and you add all those execution times of the different instructions in the sequence, then that will give the total time taken by the processor to execute this sequence of instructions. Now the question that we need to ask is the time taken to execute each of these instructions the same, right? And in order to answer that question, we need to understand what exactly is involved in the execution of each of these instructions. Okay, so we'll try to do that now. Let me just take a minute. As you have seen, there are multiple phases in the execution of the instruction. One is fetching the instruction. Then we have to perform what is called the instruction decode. We have to find out what the instruction we are executing. Then we have to fetch the operands. Then we have to perform the operations specified by the instruction. Then we write the result. Right? So typically any instruction will have these 4 major sub operations, and it all depends on how much time it takes to perform each of these sub operations. Okay. So maybe I'll stop at this point. In the tomorrow's class, we'll go into some details of how much time each of these sub operations will take, and then we'll see how we can increase the throughput by deviating from this method of sequential execution of the instructions. Yeah. Any questions? Okay. There are no questions. Maybe we'll stop here. So we'll meet at 3 o'clock today.